Hi. Today we're going to continue on talking about how measurement works in chemistry and maybe cross over with a little bit of information you've seen before and maybe a little bit of information that you haven't. So to get things started, if you'd like, hit the pause button and answer these questions. This is a quick review of, using the reference tables and converting units. We're not 100% sure what joules are yet. We haven't covered that in class. These are kilojoules. So this is a capital letter J from table C, D, D. And this is lowercase k, capital J. Again, we're putting together C and D. That means if we're looking at our answers, we're converting to kilojoules in all four, so we might as well just do the conversion. 500 joules. We've got joules, we've got kilojoules. Kilo means 10 to the third. And we get 0.500 kilojoules after we cancel, which means answer choice 3. And then we have 50 kilojoules. And again, we're doing the same process, putting kilojoules on the bottom, joules on the top as our target unit, because all four answer choices have joules. 1 kilojoule is 10 to the third joules. Multiply across, and we get 50,000 joules. And if we turn that into scientific notation, we get 5 times 10 to the fourth joules, so that's choice 4. And then, of course, if you were wondering, you go look back at table D, and it says that joules are the way to express an amount of thermal energy, which answers what joules are. So for today, actually, here's a box. We're going to talk about a box. Okay, but actually, if I were to ask you to measure the box, you might ask a bunch of questions. How big is your screen? What units of measure are we using to measure the box? So I'm going to help. There's a ruler. How long is the box? You might have a guess in your head how long the box is. I know at the very least that this box is less than 10. I don't know what that unit is because, again, I don't know how big the screen is, and the ruler is not a good ruler because it doesn't put units on it, but I know that the box is less than 10 units. Muehlek unit of distance. I like it. I'm going to call it a mud for short. Okay, so that's less than 10 mud. Same box, has not changed in size, right? The box is still the same size, but let me bring in a different unit, a different ruler with a different number of lines, with a different way to measure mud. In fact, if you go back between the rulers, I think you'll see that it's not only the same box, but the ruler has a line at 10 in the same exact spot. So this is presumably still mud, but I don't know how long the box is. But now I know. It's between 8 and 9 mud. I don't know, it's clearly not 8. It's above 8, but it's clearly not 9. This is still not a good ruler. But we're getting a little bit better. Still, same box, same mud, but now, I can get a lot more specific. In fact, if I get a little bit closer to the screen, now I can say it's in between 8.1 and 8.2 mud. So now this raises an interesting question. It's the same box each time, but the distance that I'm reporting relies more on the ruler than it does on the box, which leads to the question of how exactly we're supposed to be measuring once you get into a lab environment when you're, in the world. And so to talk about that, here's some examples. There are two kinds of instruments, an instrument being any tool that makes a measurement, that we're going to encounter in chemistry. They are analog, things like that have scales on them. Wow, that's a poor use of words. I'm going to cross out scales. Analog are things that have like lines on them. That might be better. Lines. And digital that have like a numerical readout but that don't have any lines that you do any reading from. When it comes to an analog scale, you are obligated as a chemist to read everything that the scale tells you, and because there are lines, you have to estimate the next digit. In other words, if you have this graduated cylinder and you fill it with water, if the water level falls in between two lines, you estimate one digit past what the lines say. So taking a look at this scale, I see that there are lines, that the big ones are every 5, but then there's 4 lines between them, so I know there are lines every 1 and it's milliliters this time, so that this line is in between 21 and 22 milliliters. But if you were to report the volume, you don't say between 21 and 22. You, as a chemist, have to make that estimation happen. You have to guess. Is it 21.5? Is it 21.6? I don't know. That's up to you. But even if we get slightly different answers between us, there's still a finite range. I think no one will look at that and say it is exactly 21. No one will look at that and say it's exactly 21.1, because that's not a good estimate. So you have to use your powers of observation. So I don't think I'd say that. I think that looks to me like 21.6 milliliters. And don't forget to watch out when we have a liquid like water in a container. Sometimes the liquid interacts with the container, and that's why you see that curve. It's called a meniscus, and when we're reading for water, we always read the bottom of the meniscus here, which comes over there, and that's why I got 21.6. Some of you may also feel it's 21.5, and that's fine. When it comes to a digital readout, like a scale, which is why I should not have used scale, there's nothing to estimate. Whatever object is on the scale, when it says 126.4, it's 126.4. There's no estimation to be had. In that way, you might think that an analog instrument is a little bit better than a digital instrument, but also usually the digital instruments are built to be slightly more sensitive and can give you that information just as easily. I mean, now that we've talked about how to measure, I have a nagging suspicion you can come back and say, how long is the box? And if I were to say how long is the box, knowing that I use what the instrument gives me and go one further, the instrument gives me numbers every 10. Presumably, if the ruler kept going, there'd be lines at 20, 30, 40. So I know that the tens digit is 0. That's what the instrument tells me. Now I know that the tens digit is 0, but it's obviously not 0. It's in between 0 and 10. So then I have to estimate the ones digit. In this case, I'm going to estimate that the ones digit is 8. So that's how long the box is when I use this ruler. Going back to the second ruler, now I know that, I know the tens digit is 0, but I don't really need to show that because we don't need to show those zeros out before the number starts. I know that the ones digit's between 8 and 9, so I'm going to put 8 as the ones, and I'm going to estimate the tenths digit. Again, this looks like roughly 2 tenths. So our official chemistry measurement would be 8.2 mud. And then if we were to use our third ruler to get a little bit better, I would say now it looks like if I were to draw a little bit of a line right up against the edge there, I know it's 8.1. I'm going to say it looks like it's kind of in the middle to me. So this would be the ones, this is the tenths, and this is the hundredths. So this is our estimated digit. That's the one that you provide. The ruler has lines that'll go to the tenth. So this is 8.15 mud. Now what you may notice is that based on my estimation, I said it was 8.2, then it was 8.15. There's actually slight variation there, and if your ruler doesn't have enough lines, you might have to round the true answer is actually rounded. I said that backwards. The ruler answer might be rounded from what the true answer is, and the true answer is just at the limit of whatever instruments you have. The largest application of things like reading off of scales and analog lines would be calculation of density. Obviously something you've done before. We're going to use our reference tables for this. If a substance has a regular shape, it's very easy to figure out what the volume is. Volume is length times width times height, or if it's some other regular shape, volume is pi r squared h, or whatever. But say you had some sort of irregular object like this 3D lightning bolt. Sure, the 3D lightning bolt might be some composite of regular shapes that you could calculate the volume of if you really wanted to. But then let's say you have something like, I don't know, a little plastic diver. You can't really figure out the volume by trying to add it up as a series of polygons in any sort of reasonable amount of time. So we use something called water displacement, which involves having a known quantity of water putting in your object, and then measuring the new volume of water, and you have to subtract. So what we get from our first graduated cylinder here is V sub I, or initial, which, looking at this, we have lines every we have lines every 2, so I don't quite know how to estimate that, but here's what I'll say. It seems like that's pretty spot on for 46 milliliters. And I am going to put the 0.0 there because the 6 came from the instrument, so I need to go another bit further. And it's okay if that's a 0. For this one, this final, or if you want to say V2 and V1, you can. The final is going to be, let's say, 54. Well, it's a little shy of 54. Let's say it's 53.9 milliliters. So that our volume here is going to be equal to the final minus the initial. It's always 2 minus 1, or final minus initial, or 53.9 minus 46.0, and that gives you, I can do math, 8, well no, it's not 8, it's 7.9. And then in terms of your answer, you see that the amount of information in our answer has 2 digits instead of 3, but that's still and then you can use that density in your calculations. An application here, if you want to hit the pause button and figure it out, we want to figure out the density of this piece of gold. I'm going to need my calculator, so I'm going to do that. Cancel the ball. Let me pull it up. So we have a mass given here. The volume is shown over here. We have to do some math. If you want to do it on your own, go ahead, hit the pause button, but I'm going to get started. Using our reference table, there's a formula on the back in case we've forgotten. Density equals mass over volume. In this case, we know the mass is 51.842 grams. We don't know the volume yet, but we can do that. We can figure that out by doing the same thing we did on the previous slide. Our final volume seems to be, these lines are every 1, so we can estimate. This looks like it's 19.9, I'd say, maybe 19.8, but that's up to you. And then this appears to be 16, 17. I'm going to say 17.2 milliliters. So that's going to equal 5.7. That's not 5.7. That's not 5.7 at all. I can't do math. 2.7 milliliters. To plug that, then you want to plug that back in up for your volume. Grab a calculator. And we get 19.20 grams per milliliter. For now, let's just round at a reasonable length. Let's say like 2 decimal places if you have them. That's fair, and we're not going to put any more rules on it than that. So our density was 19.20 grams per milliliter. Nope, there's my pen. You may find yourself in the position of being asked to calculate a percent error, which may or may not be a formula you're familiar with, but I wanted to take the time to mention it. There's your reference table link. On table S, we have a lot of information, standard information about elements, gold being an element. And if you forget how to calculate percent error, table T on the reference table provides all of the formulas you're probably going to need for getting through chemistry, so we can use that. So for our percent error, we're going to just follow our value. On table S, gold is number 79 in the periodic table. The density shown right there. It says grams per cubic centimeter, but 1 cubic centimeter is actually equal to 1 milliliter, so that's also 19.3 grams per milliliter. It says measured value minus accepted value divided by accepted value times 100%. And then we're just going to go through and do that math kind of quickly. 0.1. And then you're going to multiply it by 100, and what you should get is negative 0.52%. So that data was pretty good. We're pretty close to the right answer. The fact that the number is negative just means that your measured value is less than the accepted value. If you want to do the absolute value of that, you can. So to sum things up, read one decimal place past analog lines. This one decimal place is sometimes known as the uncertain digit, where the other digits that you got from the actual analog lines are called certain digits. And then to really, like another thing would be water displacement is useful. It's actually preferred to do water displacement in most cases to use your tool that has probably more specificity than maybe a ruler does to get your volume. Thanks for watching.